Bridget.
Ich habe dich bei Tinder angemeldet.
Was? Ich bin schneller da, als ich gebraucht habe, um dich zu einem markerschütternden Orgasmus zu bringen.
Du erweiterst damit nur deinen Freundeskreis. Schmeiß dich ins Kleid und lass mal wieder jemanden ein.
Alles in Ordnung, Mrs. Darcy?
Wenn Sie irgendwas verschnürt haben wollen, dann bin ich die Richtige.
Bridget Jones, verrückt nach ihm.
Oh, crap. Make me good, boy. Right on, dudes. 15 seconds, stand This is beautiful. So,
Get up now!
stop screaming, for the love of God. I was never meant to be a warrior. But adventure found me. You have to fight till the bitter end.
Okay, so I'm going to talk to you now about plutonium.
So I once referred to uranium as the boogeyman of the periodic table, but if uranium is a boogeyman, then there is a Hannibal Lecter of the periodic table, and it's a couple of places to the right, and that element is plutonium.
Plutonium has a really quite nasty reputation. For example, there's a book here, Plutonium, History of the World's Most Dangerous Element.
When the human race evolved, it evolved with uranium in the environment, so we physiologically can actually deal with it to some extent. Plutonium is a man-made element. It wasn't there in the environment when we evolved, and this means we've got essentially zero tolerance to it, so that makes it quite dangerous for us.
We're at Sellafield in the northwest of England. We're at the NNL Central Laboratory. We're interested in plutonium because we need to be able to recover it from spent irradiated nuclear fuel.
You can't just use plutonium in a regular laboratory. You have to have a laboratory which is specifically designed to handle it, so it's handled safely.
It's at the point in the periodic table where it does interesting things.
There are not many elements which you can say when they were created. You can sometimes say it was discovered in 1869 or 19 whatever, but plutonium was made for the first time in 1940. The reason that it was made is that it's a radioactive element and it decays away with a half-life that depends on which particular isotope it is. If plutonium was created at some time during the formation of the solar system, it has all decayed away long before scientists ever started looking for it on Earth.
I have seen a lump of plutonium once. I don't think I can tell you where I actually saw it, but it does just look like a shiny piece of metal. What we'll see today is plutonium in solution. And that's really interesting because plutonium's got some really intense colors, and the colors change depending on the oxidation state of the plutonium as well. It's incredibly dense as a metal. You could take to it with a hacksaw and the hacksaw blade would break before you chipped any plutonium off. The sheer density is shown by the fact that a golf ball sized lump of plutonium would be over a kilogram easily, really quite heavy stuff.
So here, the intention is to recover the plutonium from spent nuclear fuel. Plutonium is present in about 1%. What we do is use solvent extraction in order to remove the plutonium from the fission products in the aqueous phase and move the plutonium up into a solvent phase. And that solvent phase is a mixture of tributyl phosphate and a diluent called odorless kerosene. Here we have some plutonium nitrate, and this plutonium is in oxidation state 4, and that's the oxidation state that's extractable into tributyl phosphate. I've got two separate solutions here. They're both plutonium nitrate, they're just at different concentrations.
It is dangerous for several different reasons. It is dangerous because it is the basis of atomic bombs. The second atomic bomb so-called Fat Man that was dropped on Nagasaki in 1945 contained plutonium, and it was the plutonium that made it explode. It was a bigger bomb in terms of the size of explosion than the first bomb that was dropped on Hiroshima. But it's also dangerous, plutonium, because it is very poisonous. Many heavy metals are poisonous, particularly, say, thallium. But plutonium is poisonous not just because of its chemistry, but because of its radioactivity. Plutonium decays radioactively by emitting alpha particles, helium nucleus. And when that hits the cells of your body, it can cause terrific damage, and that can lead to cancer and so on.
I'm going to take some 30% TBP. So this is the solvent phase. You can see there it hasn't been mixed yet. The solvent is less dense than the aqueous phase and resides on top of the aqueous. But you'll see in a minute that brown colour will go up into the top phase.
According to this book, there is a club, or there was a club, in Los Alamos, the bomb factory, where they developed the chemistry of plutonium and made the plutonium bomb, of 4 people, which had rather a strange name. This says UPPU, which means your urine contains plutonium. And these are people who, through some sort of accident, had plutonium in their body. There was one person that was described called Margle, who was working with a glove box, just like the ones that we saw in the NNL labs. And he had, for some reason, a needle, and he stuck the needle through the finger of one of his gloves. And he pulled out his hand and saw that there was a tiny black speck in his hand, which was a fragment of plutonium. And although the doctors tried to dig this out, for the next 50 years, plutonium could be detected in his urine. And it wasn't very high concentration. According to this, he had to provide a gallon of urine, that's 4 liters, before they could detect the plutonium. But nevertheless, he survived.
Okay, so I've got 2 samples there with plutonium nitrate at the bottom and tributyl phosphate odorless kerosene on the top. So what I'm going to do now is put them into this device, which is called a vortex mixer. So while that's mixing, plutonium's going up into the solvent phase. It'll form an emulsion, and the solvent will then start to disengage from the aqueous phase, and the 2 phases will separate out.
Plutonium is formed in the nuclear fuel of nuclear reactors. Uranium, which has atomic number 92, can be transformed into plutonium, which has atomic number 94, by absorption of neutrons. So the uranium absorbs neutrons. That is the uranium-238, the sort of uranium that does not spontaneously fission and provide the energy for the nuclear reactor.
The Hanford, Washington Active Material Production Plant, where uranium-238, the most abundant isotope in natural uranium, is converted into a completely new fissionable element known as plutonium-239.
So it's the so-called, if you like, inactive uranium isotope, but that can absorb neutrons and be transformed into plutonium.
Okay, that should be done now. Looks like an emulsion at the moment. As it separates, you'll see that the top phase has now got the colour in it. The plutonium nitrate has now formed a chemical complex with TBP molecules. And those TBP molecules have made the plutonium soluble in the organic phase. In the reprocessing of irradiated nuclear fuel, all the fission products would now be in this bottom phase. And the plutonium and uranium would be in this top phase here. So you've separated them out.
Plutonium itself, the metal, is actually a very fascinating material. I've never seen it, but it's meant to be a very hard metal, but it has a surprisingly large number of allotropes. An allotrope is a different crystal structure. Plutonium has 6 or perhaps 7 different allotropes, which differ in their hardness, their mechanical properties, even their density. This makes the machining of plutonium, which is necessary for manufacture of nuclear bombs, extremely difficult. It also has quite a low melting point. It melts at 639 degrees centigrade, which is really very low melting point for a heavy metal. For example, osmium, which is not far away in the periodic table, has a melting point well above 3000 degrees centigrade. Some of the isotopes of plutonium are so radioactive that they're really quite hot. So if you feel the sample, some of them can even be glowing red hot, but even the less radioactive ones apparently feel quite warm to touch, though you have to be quite brave to touch them.
What happens in a solvent extraction process is that the solvent is separated from the aqueous phase, and then new aqueous liquor is added to that solvent to try and recover the plutonium from it. What we're going to do is remove the aqueous liquor from this now, from the bottom, and replace it with some fresh liquor that's got a chemical within it that will promote recovery of the plutonium from the solvent. And taking the aqueous phase out from the bottom. Of course, on an industrial scale, this is done with a variety of devices.
Why are you trying to get the plutonium on its own? Because it has to be disposed of in a special way, or because you want to reuse it?
It's separated and into a pure form so that it can be reused in things like MOX fuel, which stands for mixed oxide fuels. So that's where you combine plutonium with uranium, and you can put it back into nuclear reactors and generate new energy.
There is also an interesting feature that when they decay, radioactively, they give off these nuclei of helium atoms. So as you get an older and older sample of plutonium, the helium builds up in this crystal structure. So although it looks like a piece of metal, in fact, it has helium atoms inside it, rather like the fruit inside the cake. And because of this crystal structure, you tend to have crystallites with boundaries, so-called grain boundaries between the crystallites, and the helium can accumulate on the grain boundaries and weaken the metal quite substantially. The helium has two problems. Obviously, in the short term, if you are somebody who makes bombs, you have to be careful that you don't build up too much helium in the core of your bomb, because it then may not perform properly.
Here in sequence are the 4 snapper blasts, detonated atop their steel towers on the 7th and 25th of May and the 1st and 5th of June.
The second problem is that if you are storing plutonium, which has come from reprocessed nuclear fuel and is just being stored at waste until it's safe to be in the environment, you will bury it somewhere in the ground in a very strong container. And when you're designing that container, you have to allow for the fact that your metal will start producing a gas as it decays. And therefore, your container has to be able to withstand the internal pressure so it doesn't suddenly explode, which would be embarrassing, if not for you, for your grandchildren or their grandchildren when they suddenly discover that these secure containers have blown up.
Did you just describe the explosion of a container containing radioactive plutonium waste as embarrassing?
Yes.
I tell you what, right, for all the excitement about plutonium, it all looks pretty harmless there, that muddy brown solution.
Well, it's highly radiotoxic, and you wouldn't want to drink that either.
Well, I won't then, even though it looks a little bit like Coke.
In order to get that plutonium back into the aqueous phase, I'm going to use 2 different techniques. One is a reduction to get plutonium-4 into a plutonium-3 oxidation state. So what I'm going to do to this one is add a chemical called hydroxylamine nitrate. This is another method. We're using a complexant, which means that it forms a chemical molecular compound, and the chemical that we're using is called acetyl-hydroxylic acid. When we've mixed it, all the plutonium will be in the bottom. Okay, so this is the acetyl-hydroxylic acid solution, and it's just disengaging now between the aqueous and the organic phase. And as you can see, the colour in the top phase is completely gone now. So that's the solvent. Solvent is now free of plutonium, and it's come back into the aqueous phase. And that aqueous phase can then be sent to downstream plants for final purification and conversion into the final form, which is plutonium dioxide. So this hasn't been quite as effective, but you can see there the orange colour that was in the top half has been diluted now, and most of the plutonium is in the bottom half as plutonium-3.
So I have another story. I've told it before, but it's really good, and Brady wants to hear it again. One of the people who taught me chemistry, a professor at Cambridge, Alfie Maddock, worked on plutonium during the Second World War. And one night, when he was really quite tired, he spilt the entire United Kingdom supply of plutonium, which was 10 milligrams, onto the table, the bench that he was working on. He was really upset. He'd lost the whole country's supply. So he got a saw and cut a hole in the top of the table. He burnt the wood, and from the ashes of the wood, he got back 9.5 milligrams of the 10 milligrams he'd lost. And he would have hidden the whole thing, but he was so tired by then that he didn't have the energy to repair the tabletop. So when people came in the next morning, there was a big hole, and so they discovered what's happened.
So the one on the left here with the red solution is plutonium-4 with acetohydroxamic acid. On the right here, it's plutonium. The blue plutonium at the bottom is plutonium-3 that's been reduced by hydroxylamine nitrate.
Mit Salt Business können Sie grenzenlos nach Europa telefonieren. Egal wo, egal wann. Pro Europe. Unlimitierte Area von Daten in Europa. Jetzt mit 180 Franken Sparvorteil.
Добрый день, дорогие друзья. Мы снова на YouTube-канале Марка Солонина. У нас сегодня техникум. У нас продолжается бесконечный атомно-бомб.
This video is sponsored by Conflict of Nations, the free online strategy game where you get to find out what it's like to take control of a real country and lead it in modern global warfare. You'll take on up to 128 other players in real-time games that can take weeks to complete, using armies filled with diverse units like powerful tanks, jet airplanes, and even nuclear submarines. But there's more than just fighting on the battlefields. My favorite part of the game is the social strategy side, forging alliances and declaring war on other real players. It's fully cross-platform, so you can play on the same account on PC and mobile. We'll be hosting a custom game for the first viewers that click the link in the description with instructions on how to join at the end of the video, so make sure you stick around. Infographics show viewers also get a special gift of 13,000 gold and 1 month of premium subscription for free when they use the link. It's only available for 30 days, so click the link, choose a country, and start fighting your way to victory right now. On August 6, 1945, an American B-29 bomber flying low over the Japanese city of Hiroshima dropped the world.
Backup und Restore von Proxmox VE-Umgebungen. Klaus, der SEP-Erklärbär, steht vor einer Herausforderung. Seine Kunden benötigen zuverlässige und effiziente Backup-Lösungen für ihre Proxmox VMs. Hier kommt der SEP Proxmox-Agent ins Spiel, der mit beeindruckenden Funktionen aufwartet. Der Agent unterstützt Storage-Snapshots von blockbasierten Storage-Typen wie LVM-PIN, ZFS und CephRBD, was die Grundlage für Online-Backups bildet. Proxmox-Nutzer dieser 3 Storage-Typen können sich als besonderen Bonus sogar über die Möglichkeit des Single-File-Restores freuen. Diese Snapshots
First atomic bomb on the city's unsuspecting inhabitants, immediately killing 80,000 innocent civilians. 3 days later, a second bomb was dropped in the city of Nagasaki, killing a further 40,000 men, women, and children. In the aftermath of the bomb's initial explosions, tens of thousands more people would die excruciatingly painful deaths due to radiation exposure. While the world may be familiar with the tragic story of the first use of the atomic bomb, we are less familiar with exactly how it works. The atomic bomb was a devastating act of cruelty, but also a technological marvel that would forever alter the face of war. The devastating bombing of Japan was enough to deter the use of nuclear weapons for at least a few decades. But after World War II, increasing tension between the US and Russia led to the Cold War, a nuclear arms race between the two world powers that saw both sides rushing to increase their stockpile of nuclear weapons, ostensibly as a means to deter war. People built bunkers in their backyards and stocked up on canned goods. Schools ran nuclear war drills, and the world waited with bated breath for the outbreak of nuclear war and what felt like the imminent end of the world. But although the existence of nuclear weapons was common knowledge, and despite the widespread panic about the nuclear war, few people truly understood just how an atomic bomb works. To understand how the atomic bomb works, we have to take a trip back to high school physics class to revisit the concepts of atomic structure and radioactivity. An atom is one of the smallest units of matter, and it's made up of 3 subatomic particles. The nucleus at the center of the atom is made up of protons, which are positively charged, and neutrons, which have a neutral charge. Negatively charged electrons orbit the nucleus of the atom. When the ratio of protons to neutrons is 1:1, the atom as a whole will have a neutral charge. But if the number of protons in an atom is changed, an entirely different element will be created. If the number of neutrons changes, you end up with an isotope. For example, the carbon atom has three naturally occurring isotopes in its common stable form. Carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons but 7 neutrons. And while rare, it's still a stable element. Carbon 14, with its 6 protons and 8 neutrons, is both rare and unstable, or radioactive. Radioactive nuclei emit particles called radiation through a process called radioactive decay, and it's this process that scientists harness to create the powerful atomic bomb. There are a few different ways to destabilize a particle, but for understanding how nuclear bombs work, the most important processes to grasp are fission and fusion. Fission involves splitting the nucleus of an atom in two, which scientists can do by bombarding it with free neutrons. As the nucleus splits, it ejects neutrons along with bursts of electromagnetic energy called gamma rays. Fusion, in contrast, involves bringing together the nucleus of two atoms to form a single larger one. This is actually the process by which our sun produces energy. Through endless experimentation and a process of trial and error, scientists eventually discovered that uranium was the element that was most cooperative in inducing a fission reaction. The isotope uranium 235 is one of the few materials that can be forced to undergo fission by bombarding its nucleus with neutrons, rather than waiting 700 million years for it to decay naturally. U-235's nucleus will readily absorb the neutrons, become unstable, and split, throwing off 2 or 3 new neutrons in the process. Those new neutrons can then go on to collide with the nucleus of other U-235 atoms, starting a fission chain reaction. The splitting of the nucleus happens incredibly quickly, in the order of picoseconds, or 0.0000000000001 seconds. Yeah, that's 11 zeros. The scientific principles underlying the atomic bomb had been well known since Einstein's days, but they wouldn't be successfully applied and weaponized until the Second World War. In the 1930s, Italian scientist Enrico Fermi successfully bombarded elements with neutrons, transforming them into new elements. And shortly thereafter, German scientists Otto Hahn and Fritz Strassmann were the first to fission uranium by bombarding it with neutrons, producing the radioactive barium isotope. These breakthroughs led the scientific community to wonder if it would be possible to create a fission chain reaction that could release enormous amounts of energy that could be harnessed and weaponized, an idea that greatly intrigued the world's governments, who were in the midst of fighting World War II at the time. In an effort to be the first to weaponize fission and beat the Nazis to the punch, the US government recruited the brightest minds in physics from all over the world and launched the secretive Manhattan Project with the goal of creating the world's first functional atomic bomb. In 1941, scientists at Columbia University tried to initiate a chain reaction using uranium 235, but failed. Shortly thereafter, Fermi, now working for the US at the University of Chicago, successfully achieved the world's first controlled nuclear chain reaction in his lab underneath the school's squash courts. Also in 1941, Berkeley scientists discovered a new element, element 94, with nuclear fuel potential, which they named plutonium. With these discoveries, the race to develop a nuclear bomb was on in earnest, and within just a few short years, the world's first nuclear bombs would be used in war. Understanding the concept of fission was only part of the problem. Figuring out how to weaponize it and construct devices to harness atomic power was a whole other challenge. Critical mass is the minimum amount of material needed to sustain a chain reaction, so to harness the nuclear power, the nuclear fuel has to be kept in separate subcritical masses that won't support fission. When it's time to detonate, the subcritical masses are brought together to form a supercritical mass, and free neutrons are introduced to jumpstart the fission process. A small pellet made of the elements polonium and beryllium serves as the neutron generator, and the entire reaction is confined within a dense material called a tamper, usually made of another uranium isotope, U-238, to reflect the neutrons back into the core and slow.
Wenn Sie über den Kauf einer Solaranlage nachdenken, lassen Sie es. Denn die Regierung will sie buchstäblich für Sie kaufen, wenn Sie sich 60 Sekunden Zeit nehmen, um unten ein paar Fragen zu beantworten. Hallo, wenn Sie ein Hausbesitzer in der Schweiz sind und gerne mehrere tausend Franken bei Ihrer Stromrechnung sparen möchten, wird Sie die aktuelle Ankündigung der Schweizer Regierung begeistern. Vor ein paar Tagen hat die Regierung ein neues Energiegesetz veröffentlicht mit dem Ziel, so viele Schweizer wie möglich zu ermutigen, auf erneuerbare Energien umzusteigen und auf diese Weise zu einer sauberen Umwelt beizutragen. Durch 80% günstigeren Solaranlagen und bis zu 30% Steuerrabatt auf Material und Installation.
The core's expansion to ensure that as much fission as possible happens before the bomb explodes. Scientists developed two trigger systems for the first atomic bombs. Little Boy, the bomb dropped at Hiroshima, was a gun-triggered bomb with a 14.5 kiloton yield, equal in power to 14,500 tons of TNT. Little Boy was 1.5% efficient, meaning that 1.5% of the material fissioned before the bomb exploded. In a gun-fired nuclear weapon, a bullet of uranium-235 is placed in one end of a long tube packed with explosives, which will fire the bullet down the tube where it collides with the neutron generator, initiating fission and starting the chain reaction that'll lead to the bomb's explosion. In contrast, Fat Man, the bomb that was dropped in Nagasaki, was an implosion device with a 23 kiloton yield and 17% efficiency. Much more effective, but also much more complicated to make than Little Boy. Implosion bombs feature a sphere of radioactive U-235 as the tamper around a plutonium-239 core. The entire sphere is surrounded by high explosives, which when detonated create a shock wave that compress the core and initiates the fission chain reaction. In the wake of World War II, scientists recognized that fission bombs were wildly inefficient and turned their attention to fusion next. Fusion bombs, also called thermonuclear or hydrogen bombs, rely on the hydrogen isotopes deuterium and tritium as fuel, and can yield up to 10,000 kilotons, making them up to 700 times more powerful than the Little Boy fission bomb. Hydrogen bombs combine fission and fusion to achieve a more powerful and more efficient explosion. Within the bomb's casing is a tamper made of U-235, which is packed with hydrogen isotope fuel, and surrounds a hollow rod of plutonium-239 at the core. An implosion fission device detonates first, compressing the fuel and causing the plutonium core to fission. The fissioning rod in turn gives off heat and pressure, which initiates fusion in the hydrogen isotopes and causes the bomb to explode. The entire process takes just 600 billionths of a second. Not only have the bombs themselves improved drastically, but the delivery methods have come a long way since World War II. Philip Morrison, a former member of the Manhattan Project, told Scientific American in 1995 that all three bombs of 1945, the Trinity test bomb and the two bombs dropped on Japan, were more nearly improvised pieces of complex laboratory equipment than they were reliable weaponry. Today, nuclear weapons come in many forms, from ballistic missiles that can exit the atmosphere and travel thousands of miles before re-entering and detonating, to cruise missiles, shorter range missiles with smaller warheads that are harder to detect and intercept. to a range of tactical nuclear weapons like artillery shells and landmines that can target a smaller area. Nuclear weapons are terrifying because of their immense destructive power relative to their size. The most severe damage happens at the blast's hypocenter, or ground zero, where everything is immediately vaporized. Outward from the center, most of the damage is the result of flying debris, intense heat, a powerful shock wave, and acute exposure to high radiation. Beyond the immediate blast area, death and injury can result from heat and resulting fires, as well as from radiation. The physical destruction caused by a nuclear bomb is no doubt catastrophic, but the most dangerous part of a nuclear bomb is the radiation and radioactive fallout. After the initial explosion, clouds of fine dust made of radioactive particles are carried away by the wind and fall back to the ground, poisoning the water supply and getting ingested and inhaled by people even miles away from the blast. We now know that radiation affects the cells in our body that readily divide, like hair and gut cells, bone marrow, and reproductive organs, leading to nausea, vomiting, and diarrhea, and long-term health consequences like cataracts, hair loss, loss of blood cells, and an increased risk of leukemia, cancer, infertility, and birth defects. At the height of the Cold War in the 1980s, scientists warned about the danger of a nuclear winter